But our more general case, Biot Savat. And in the Biot Savat law, I like this picture very much. We have is dB. This is a little tiny bit of magnetic field due to a little element of current. So we've got this little tiny baby length of current, a dl, infinitesimal amount of current, is going to produce a little tiny dB. And then we'll have to sum this up to get the total magnetic field by adding together all the little elements of current that have different physical orientations with respect to one another. So it looks like this. Mu0 I over 4 pi times dl cross r hat over r squared. Here dl is equal to our little element of current. And r hat is a unit vector that goes from dl toward the point where the magnetic field is being calculated. So it takes a little bit of thinking and orientation to understand what this means. And so before, remember that for the electric field problems, the first kind of problem we started with, which I think most people would agree is the simplest kind of problem, is the electric field for a thin ring. Remember, that's how we started, because that has the least mathematical complexities and can give us the idea of how to apply the technique without getting into a lot of problems. And so here, instead of a ring of charge, what we're going to start with as our simplest example is a current loop, a single current loop. And so let's say that our goal in this problem, and as we go through this, we'll see how to apply the Biot Savat law. And then I'll show you how to do it for other problems. This doesn't have the right kind of symmetry, by the way, to calculate this using Ampere's law, because you don't have a uniform magnetic field through the center. When you had an infinite number of these terms, then you had a uniform magnetic field that could constructively interfere with all the other current loops. But when you look at a single one, that symmetry is destroyed. And it's no longer a semi-infinite approximation. Wrong symmetry. Everything's wrong for Ampere's law. And so you'll get used to which kinds of problems work better for the Biot Savat law and which ones work better for Ampere's law. Because we've already looked at most of the ones that you would see using Ampere's law. And the rest of them are going to come into this category. Okay, so what I'm going to do then is draw a picture. I don't like the perspective pictures here as well. What I'd rather do is have this thing, and this is a thin current loop. Okay, so by thin here, I mean that the wires are thin. It doesn't have an inner and outer radius to this current carrying wire. And it has a radius r, the loop does, and current that I'll just call I. So the current I is flowing through. This isn't a magnetic field. This is the current that produces the magnetic field. So what we did before was kind of a shortcut. We said, okay, well, I'm just going to stick my thumb in a direction. I'm going to curl my fingers around the wire, and I'm going to get the magnetic field. But here we've actually got to do some work. We've got to calculate. Okay, so let's do that then by taking a little element of current. Here, I'll call it DL. And so IDL then is a little tiny length of current, IDL. And then R hat is going to go from the DL toward the point where I'm calculating the magnetic field. So let's say we want to find the magnetic field at the center. So this is where my little dB is going to be, is in the center. So I'm looking at how much current here affects and produces the magnetic field there. Okay, and so we can say, well, I already know which way it's going to point because I can stick my right thumb in the direction of the current. I can curl my fingers around the wire and I can see that it's going to come out. And that's a good way to check it. But here, what you need to do instead of that is say that the magnitude of DL cross R hat is equal to the magnitude of DL times the magnitude of R hat times the sine of the angle between DL and R hat. So that's just equal to DL sine theta. Because the magnitude of a unit vector is just 1. So that means that the magnitude of dB is going to be equal to mu 0 I over 4 pi times dl sine theta over r squared. So we use this to get the magnitude. We use this to get the direction. So we do this using our right-hand vector cross product. Do dl. So we stick our arm in the direction of dl. That's the first thing. And then we curl our fingers in the direction of the second vector, dl cross r hat. And so that's the real reason why the magnetic field is coming out of the board, is that we found our dl, we found our r hat, we did the vector cross product of them, and we got the direction for dBs out. So one of the difficulties with this kind of a problem is that sometimes different current elements may add or subtract in terms of the contributions to the magnetic field. Remember, we saw that with electric fields. Some of the components of electric field would add and some would cancel depending on the situation. So we have to double check that that's not the case here. So what I'm going to do is I'm going to find another spot, another arbitrary spot, with my little DL there, which is, I'm drawing it in the same direction as I, and then the R hat is going to point in this way. Because remember, R hat is a unit vector that goes from the DL toward the point where we're calculating the magnetic field, dB. And so if we do that again here, we get DL this way, cross R hat, pointed in the same direction. So we're okay. We're good to go. We don't have a magnetic field that's partially canceling itself out as we go around this loop. They all add in the same direction. So we don't have any cosine theta things that we've got to throw in because of partial cancellation of the magnetic fields. So that means we're good to go. So now we can plug in, and we know that this is equal to the sine of 90, because in this case, theta is 90 no matter where you are on this thing. DL is going to be pointed perpendicular to R hat. DL, R hat. Always 90 degrees. Over here too. DL, R hat. Always 90 degrees. So we can then write that the magnitude of dB, now we're going to try to integrate this thing, is mu 0 I over 4 pi times dl over r squared. Okay. And And so if we're integrating all the way around this thing, what's the integral of d? And r is constant in this case. So we can write this as mu 0 I over 4 pi r squared. That's the integral of dl. What are we going to get? 2 pi r. Okay, now if we want to here, we can write this as r d theta. I was skipping this step before, but if you do it this way, then one factor of the r is going to cancel, and you just have the integral of d theta. And so that either way, this is from theta equals 0 to theta equals 2 pi. It's going to be mu 0 I over 4 pi r squared times 2 pi r. And so that's just mu 0 I, and then one factor of r is going to cancel. And so the pi's are going to cancel, and we get mu 0 I over 2 pi r. So that's our total magnetic field at the center. And that would be times some unit vector that pointed out of the board, whatever direction that is. Any questions about that? Yeah.
Can you do that with divergence?
You could say that the what, del dot b is something, you mean?
Yeah.
You can, but that would get back into Ampere's law if we try to do it that way. You could write the equivalent of this. And you'd actually be dealing with a curl. It'd be del cross B would be mu naught times the current density. And then that would be the equivalent of Ampere's law in integral form. So if we write this by multiplying by an area, and then we can do something with this, del cross B d volume or something, and we can go through and we can convert one to the other.
Okay.
But that wouldn't be so good here, because here we don't have the kind of symmetry which Ampere's law, or that form of Maxwell's equations, gives us the easiest solution. It's not that it won't work, it's just not the best, easiest way to handle the problem. Okay, so that's what it would be then if we went around a whole circle. What if we had something like this, where the current segment comes in, and then around like that, and then up? And we want the magnetic field here. Real typical kind of a midterm question. Let's say this length here is L, this radius here is R, and this length here is L again. This may look like the problem that I just gave you, but it's not the same thing. In that case, what we want is the force if you have a pre-existing magnetic field. Here, what we're looking for is the magnetic field here. So what are we going to get from section 1 and section 3? Good. Why would we get 0? This is dl, and then this is r hat. So dl and r hat are in the same direction. So if you extend the line of the current through the point, you're always going to get a magnetic field that's 0, because dl cross r hat is 0, because this is basically dl sine theta, and theta is 0. So there's no magnetic field for a length of wire where the extension of that length goes through the point. Similarly here, dl is this way, r hat is this way. And so that's still the sine of 180. Okay, and so there's no cross product for dl and r hat along those top two segments. And so the only segment left is this middle segment carrying a current I. And so how is that different from this problem? It's just a quarter of the circle, do you see? But all of the little elements are adding up and pointing in the same direction. So that means that it's just going to be 1/4 of this result, or mu 0 I over 8r. Let's go through the details. Everything that we did here would stay the same. For this little element, this would be dl, this would be r hat. This would be the point where our dB is located. The only thing that's changing now is that we're integrating theta from what to what? Okay, or if you want to redefine theta to be 0 there, it would just be 0 to pi over 4. Pi over 2, sorry. 0 to pi over 2. And so what would that give us here? That would just give us pi r over 2, or 1/4 of 2 pi r. Does everybody see that? Am I going too fast? It's just 1/4 of what it was before. Limits of integration, instead of going from 0 to 2 pi, from 0 to pi over 2. Just 1/4 of the angle. It's r d theta, so it's just pi r over 2, 1/4 of 2 pi r. So that would make this mu 0 I over 8r. And that would be your answer to this problem. The part of it that's kind of conceptual is just seeing that the extensions of those lines go right through the point, and so therefore don't contribute anything to the magnetic field at that location. The only thing that's left is the magnetic field at the center of this quarter circular loop. Any questions about that? Okay, so I think I've done enough. On Thursday, we'll go into a lot more detail on how to integrate. Then also on Thursday, I'm going to introduce induction, which we looked at in lab last week. But induction is chapter 30, so that will not be on the midterm. So after I'm done looking at more of these calculus level magnetic field calculations on Thursday, we'll get started with induction, but that's where I'll draw the line for things that you have to prepare for the midterm. And so I'm also going to add this week some problems to do in lab that'll be due on the day of the midterm. And that's to give you more practice with all of this. And so here are the problems for today, but then I'm going to add to these, and these will all be, well, this one is going to be due with your lab this week, but the rest of them will be due on the day of the midterm. Okay, so here's the first one. We've got a charging RC circuit, and we want to find the time when the voltage drop across the resistor is the same as the voltage drop across the capacitor. And then you have a couple of choices here, so you can see whether or not you're getting one of those. And so once we close the switch, the capacitor is initially in charge. And so you've got V equals V max times 1 minus e to the minus t over RC power. That's the voltage across the capacitor. You have Q equals Q max times 1 minus e to the minus t over RC power. Now the current is dq dt. And so if we take the derivative of this with respect to time, we'll get e over r times e to the minus t over RC power, or I naught e to the minus t over RC. C. So that's the current as a function of time. It's just the derivative of our charge function. And I can go over the details of that, but it's basically just taking the derivative of this expression with respect to time. So the first term would drop out, then you'd have a minus here, 1 over RC times Q max. That Q over C is just your total voltage, E. Okay, so when you do this, and you get Q max times 1 over RC times E to the minus T over RC power, that's going to be Q over C times C. And so that'll be CE, or E over R. And so I can go over that with you if you're not clear about that. But what you need to do then is say, well, IR has to equal Q over C. Because we want the voltage drop across the resistor to equal to the voltage drop across the capacitor. And so what time does that happen? So that's problem 1. Problem 2, one of my favorite all-time problems. We've got a cylinder that has N turns of wire wrapped around it, and it's sitting on an inclined plane. It has a bunch of current flowing through the turns of wire, which are along the axis of this thing. So the currents are going along there through the front, then they're following along like this through the back, and then they're going back like this, and then back up like that in the front. And so that generates a bunch of little current loops. So these current loops, remember, have a magnetic moment. It's equal to NIA times some unit normal. And torque is mu cross B. So then you have to equate that with the torque due to gravity. So mg is going to be acting down this way. But the component of mg that's acting down the incline will be mg sine theta, and then that'll act through some radial distance r. So you need to set those equal to each other and then find the current so that this thing will hold itself in place. So that's problem 2. Problem 3, this is very much like the problem we just looked at, where you've got a wire loop and we want the magnetic field at the center. So you're going to need to figure out this contribution and that contribution. My intuition tells me they might tend to cancel. And then you also have to figure out what the magnetic field contributions are due to these sections here. What would you say those are? 0, because if you extend the line of these two, they're in the same direction. So the dl and the r hat are in the same direction, or opposite each other. So only these sections then should contribute, and it'll be something like what I did there, but you just have a different limits of integration. Looks like they're going to tend to subtract. So be sure that you try to get the right direction for each one. And we have our tutors here to help too, so this is, I think, a good start to getting ready for the magnetism part of the midterm.